So let's start looking at aromatic compounds. Aromatic compounds, as you already know, are otherwise known as a range, and they include benzene and benzene derivatives. Examples of aromatic compounds in addition to benzene include things like toluene, orthoxylene, phenol, aniline, benzaldehyde, benzoic acid. These are just some examples. Now, many aromatic compounds were originally isolated from fragrant oils. In other words, they had great flavors. However, interestingly, many aromatic compounds are odorless. They don't really have any odor. Now, aromatic compounds are quite common. In fact, about 8 out of the 10 certain drugs have aromatic moieties. Examples include Nexium, which is also known as omeprazole, or Zoloft, used in the treatment of depression. Now, coal, as we already know, contains aromatic rings fused together and joined by non-aromatic moieties. You can see that these fused aromatic rings are joined by functional groups like sulfides, amines, ethers, amides, right, alkanes, so basically that's what these are. Now, benzene is generally the parent name for mono-substituted derivatives. For example, we have things like chlorobenzene, nitrobenzene, ethylbenzene. These are all considered to be derivatives of benzene, where benzene is the parent name. However, many benzene derivatives, especially mono and disubstituted benzenes, have common names. Okay, and for some of these common names, the common name becomes the parent name. Examples which I want you to become familiar with are things like toluene, phenol, anisole, aniline, benzoic acid, benzaldehyde, acetylphenone, and styrene, which is the monomer for making polystyrene. Okay, so you need to learn these. That's what I will tell you. You need to learn this. You need to become comfortable with these common names, because these common names will take on the parent names even in the IUPAC system of naming aromatic compounds. Now, generally, when naming aromatic compounds, if the substituent is larger than the ring, the substituent becomes the parent, and this is something you already know. For instance, if you look at this example here, you can see that the benzene has less carbons than the heptane, which has a total of 7 carbons. So in this case, the benzene becomes a substituent, and that substituent is known as the phenyl group. So this is 1-phenylheptane. Now, aromatic rings are often represented with pH for phenyl, or the phi symbol. You can use that as well. For example, you can see this example here. This would be 2,3,4,5 tetraphenyl cyclopenta 2,4-dienone. You see, so you can see that when the benzene is a substituent, whereby one of the hydrogens has been substituted, it becomes a phenyl group. Okay, so make a note of that. Phenyl groups. Know that benzene is C6H6, but when one of the hydrogens has been replaced, then it becomes C6H5, and that is referred to as the phenyl group. So a phenyl group is simply C6H5. Now, nomenclature of benzene derivatives. Now, when you have disubstituted derivatives, okay, for example, you have disubstituted 1,2-dimethyl benzene, that's called orthoxylene. If it's 1,3-dimethyl benzene, that's methoxylene. While it's 1,4-dimethyl benzene, becomes paraxylene. Now, what do we mean by orthometa and para. It's very simple. This is used when you are trying to name di-substituted benzene. See, when you're trying to name di-substituted benzene, that's when you need to use auto-para. For instance, auto simply means 1, 2, meta means 1, 3, para means 1, 4. And that's basically what it's trying. But this is used only when naming di-substituted benzenes. Now already we know that you can make benzene if you try to do the cycle trimerization of acetylene. If you have started with 3 units of acetylene, you can easily make benzene. And if you start out with 3 units of diphenylacetylene, you can actually make the hexaphenyl benzene, which is really insoluble. It's a very insoluble compound. Nomenclature of benzene derivatives. Of course, you identify the parent chain, which is the longest chain, right? And then you identify the name and name the substituents, and then you number the parent chain and assign a locant to each substituent. Give the first substituent the lowest number possible. Of course, remember when you number, you want to number in such a way that you get the least numbering possible. And then you place the substituents in alphabetical order in front of the parent name. And basically, that's how you get that. And nomenclature of benzene derivatives. Now, locants are required for the rings with more than 2 substituents. So if you have more than 2 substituents, you need locants to tell you exactly where the substituents are located. Now, if you look at this compound here, you can see that the parent is a phenol. So this is a phenol. So that means the carbon bearing the OH takes carbon 1. Then you have carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So, and you can see that the bromines are at the 3 and the 5 position. So as a result, the name becomes 3,5-dibromophenol. Okay, that's basically how you do it. So it becomes 3,5-dibromophenol. These are some more examples here. This is benzaldehyde. You can see the parent here is benzaldehyde, and the chlorine is at the 4 position, because if you count 1, 2, 3, 4, 5, and 6, you can see that the chlorine is at the 4 position. So it becomes 4-chlorobenzaldehyde, or you can call it para-chlorobenzaldehyde. You see, now here in this case, the parent is toluene, and the bromine at the 3 position, because you have 1, 2, 3, 4, 5, and 6. So because the bromine at the 3 position becomes 3-bromotoluene, or you can call it meta-bromotoluene, because the bromine is 1,3 with respect to the methyl group. So it becomes meta-bromotoluene. Okay. In this example, you can see that the parent is anisole. It's an anisole. And you have the nitro group in the 1 position, in the 2nd position. That's 1, 2, 3, 4, 5, 6. So you can see that because the nitro group is in the 2nd position, it becomes 2-nitroanisole, or you can also call it ortho-nitroanisole. Remember, you only use auto, meta, and para when you are looking at di-substituted benzenes. You don't use auto and para when you are looking at tri-substituted or mono-substituted benzenes. You don't. Okay, so make a note of that. Now, in 1866, August Kekule proposed that benzene is a ring comprising of alternating double bonds and single bonds, right? And the evidence is by looking at the carbon-carbon bonds, and experimental evidence suggests that the bonds are neither they're neither the bonds are neither double nor single. You see, they are neither double nor single. Okay, that means the actual structure is somewhat in between, and that's why you have to use two Lewis structures to describe the actual structure of benzene. Okay, so the calculated structure suggests that the exchange of double bonds and single bonds was an equilibrium process. Yeah, but you can see that you're actually using two Lewis structures to describe the actual structure of benzene. Now we know that aromatic structures are resonance contributors, right, rather than in equilibrium. Okay, and of course you know that resonance is different from equilibrium. In resonance, you're simply looking at multiple Lewis structures to help describe the actual structure of an organic molecule. However, in equilibrium is a dynamic state where the rate of the forward reaction becomes equal to the rate of the reverse reaction, or is a steady state in which the concentration of the products and reactants becomes constant over time. But you can also say that the energy of the system is at a minimum. So these are all simple requirements, for a system to be at equilibrium. And so, going back to resonance, you know that resonance is simply using multiple Lewis structures to actually describe the actual structure of the molecule. And so that's why we have to use two Lewis structures here to describe the actual structure of the molecule, because one Lewis structure will not be sufficient. And so you can see how we use those two Lewis structures here. So this will be considered to be the hybrid, because this is showing the bonds as neither single nor double. But I want to say that when you're describing benzene, make sure you don't use this kind of structure. Make sure you use either this or you can use this. Okay, so this is just something I want to give you a heads up. Now, benzene, as you already know, has exceptional stability, and that's because it's aromatic. Okay, if you remember when we looked at the chemistry of alkanes, we know that alkanes will undergo addition reactions, right? To get you can add a bromine here, and you get the dibromo compound, which of course adds in an anti-fashion, an anti-addition. Okay, aromatic rings are stable enough that they don't undergo such reactions. Right? They don't undergo addition reactions. So if you try to carry out an addition reaction in the presence of, say, bromine and an aromatic ring, you get no reaction. The only way you're going to be able to get a reaction is if you use a Lewis acid, like a potassium tribromide. Then you get the bromobenzene. Now, you need a Lewis acid like iron 3 bromide to have a substitution, and we're going to consider the mechanism, but not now. But you just want to see that what I just need to tell you is that the stability of benzene, right, is shown by looking at the heat of hydrogenation. You see, if you look at the heat of hydrogenation, you'll be able to tell that benzene is actually more stable than we expect. For instance, if you look at cyclohexene, right, and if you hydrogenate cyclohexene by adding 1 mole of hydrogen, you get 120 kilojoules per mole of heat that is released. Right? Now, if you now look at the diene, right, you have negative 232 kilojoules of heat that is released, as opposed to we expect negative 240. Okay, that means that because we get less heat, right, it simply suggests that conjugation imparts stability to the molecule. Now, when we look at cyclohexatriene, we expect that negative 360 kilojoules is released, but interestingly, only 208 kilojoules is released, which suggests that this aromaticity imparts significant